Welcome. In this session, we'll review what we mean by a minimizer and a minimum. In this course, we'll often use vectors that are in a vector space. The way that we'll write that is we'll often use a symbol W, and we'll say that W is in an n-dimensional vector space, which means that W has n entries. We'll use a function, and by a function, we mean a map from a vector space to a real number. We'll usually write this in functional notation, and that is we'll say f has a vector argument. From these preliminaries, we can now start to talk about what we mean by, for example, a global minimizer. So a global minimizer, very simply, is a special argument W star. And W star is a global minimizer of f, means that if we take any vector whatsoever in the vector space and we evaluate the function at any vector, that the value we get is always greater than or equal to the value that we get at the minimizer. So we'll often use a minimizer, and this is a global minimizer. We can define this more formally, if we want, simply by using mathematical notation. The next term that we want to think about is a strict global minimizer. So the difference between a strict global minimizer and a global minimizer is that in a strict one, instead of having an inequality, which is greater than or equal to, we have a strict greater than. And now what we have to be is specific. We have to say for any W other than our W star, if we evaluate the function at any other vector in the vector space, that its value is strictly greater than the value of the function at the strict global minimizer. So we can take these definitions and we can now make them formal by simply using mathematical notation. So here in this mathematical notation, what we're saying is that if W is any vector in the vector space and it is not the strict global minimizer, then, and we have the same condition that we had when we were speaking informally. A global minimum is closely related to these ideas. A value L is a global minimum of a function, means that for some global minimizer, now there might be one, there might be two, there might be an infinite number of them, but for some global minimizer, L is the value that it takes on. And we'll often refer to L as a level, which is why we're going to use the symbol L. And we'll say that L is the lowest level that the function can take on, or the lowest value that results when we evaluate the function at a vector. And if we want to go to a local minimizer, now what we mean is for any W that is close to W star, that that the function evaluated at it is at least as large as the function's value at that local minimizer. And formally, you can see our notes for that. Informally, what we're saying is that W star, that local minimizer, is inside a small open set, and that everything inside that open set is guaranteed to evaluate to a value greater than the value at that minimizer. And similarly, we can say that it's a strict local minimizer, and now instead of having that inequality, we have a strict inequality.